Okay, so as we said, after cloud computing smart infrastructure, we're going to take smart transportation as an example of a smart infrastructure. We've done two activities. The first one, you all headed down to the Galbraith lobby and came back in one queue. In the second one, you split into two groups and used different routes. You split into two different routes using the north stairs and the south stairs and came back. I have the results here. They're interesting. For the first activity, the first person who came back was at 1 minute and 20 seconds. And the last person was at 2 minutes and 40 seconds. For the second activity, the first person came back again at 1 minute and 20 seconds. So that's the fast person at the front, and there's no one ahead of him. And the last person came back at 1 minute and 50 seconds. Although you were a bit tired, right? So that's interesting, and it takes us right into transportation and the problems we have in transportation. So first of all, if you know that there are multiple routes, there's a possibility that you might reduce your travel time. Okay? So your travel times, for most of you, got reduced in the second one because you knew there was another route. And another note is that selfish driving, so which means usually using the shortest route. The shortest route now was the first route that you took, does not always lead to the best outcome. So as we saw, there were people arriving in 2 minutes and 40 seconds. While if they knew about another route, which was typically a bit longer, they ended up arriving sooner. Okay? So let's see, before we go to that, some of for the first activity, what are some of the things that you noticed? Some of the students that were towards the end. Were there people in front of you? Like, could you not go ahead of them? What was happening? Why were you slow? What did you notice? Were you waiting for other people? Were you just walking? Yeah. Too many people, too narrow a space. So you had a limit on the capacity. And what else? Yeah. Okay. So if there's someone ahead of you who is slower than you, that slows you down, and then you slow down, that is in transportation called a shock wave. So a shock wave gets sent backwards where other people have to slow down. And you need to keep a safety distance, right? For cars, it's, let's say, 2 seconds. 2 seconds of how far the vehicle can go based on your speed. For humans, it's, again, something similar. You don't want to be bumping to the person in front of you, especially not on stairs. OK, so that's an important aspect of transportation. We'll see here. So one analogy of roads is rivers. So if the river has a small flow, then everything's fine. It's going pretty fast. But when you have more water coming, then the water level will rise. And if you have something limited, you have a bottleneck somewhere where the capacity can't go more than a particular limit, then eventually the water will overflow and water will spread across the land. Okay? So that is when you exceed capacity. Okay, so let's try to understand this from what's actually happening in transportation. So we're going to discuss some of the basic elements of transportation, and then we're going to go into intelligent transportation systems and how some of the newer technologies help solve the problems that we have. So there are 3 different important measures in transportation that are used all the time. One of them is traffic density. So if you have a section of a road, the traffic density is the number of vehicles that are there per unit length. So it's vehicles per kilometer. You get, let's say, a kilometer of the highway stretch, count how many vehicles you have there, and then you divide. That's how you get density. Then density is defined as, notation is raw, or K is another notation for density. So this space variable over a section. Now, another notion is speed. Okay, so we're talking about having to reduce your speed because the person ahead of you is slower. So speed is measured at, again, over a section. So you get the speeds of different vehicles or different people running, and then you average over them. And there are two ways of averaging them. I'll show you those later. So it's, again, over a section. And it gives you in kilometers per hour or meters per second. And another important element is called traffic volume. So with traffic volume, you are looking at one point of the road. Okay, let's say you are here, and you're trying to see at this point how many vehicles are going through per time. So if it's per second or per hour. So you stand there and count. Every vehicle going through, you count it over an hour, and then you divide per 1 hour. So that unit is number of vehicles per time. Okay, so vehicles per hour. So the units are very important. If you know, if you want, not sure what you're working with, and you're going to be doing calculations with these in the afternoon. If you don't know what you're working with, making sure of the units is very important. An important note here, the notion of capacity in transportation is defined in a similar way. Okay? So it is not defined over space. It is not defined over how many vehicles I can put in a space. It is defined similar to the notion of volume. So at a point of time, what is the maximum number of vehicles I can get across? Okay? That is an important distinction in transportation compared to other fields of engineering. It is again defined with these units, vehicles per hour. And common capacities are, for example, for highways, they're 2,000 vehicles per hour per lane. So every lane can, at maximum, get across around 2,000 vehicles. These are at speeds in Canada. And if you have multiple lanes, then your capacity gets multiplied by that. Okay. Now, what we typically do is you choose you can't look at one small space right away, right? So you choose a very small time. So as long as that time is small compared to maximum speed, and basically that is so that one vehicle cannot cross between these sections within one step. You do the analysis. Okay, so as we said, raw is the number of vehicles in that section, so that's the density. V is the mean speed in that section, and Q is the number of vehicles exiting the section over the sample period A. So you get each of these sections. You can measure the density, you can measure the speed, and you can also measure how many vehicles are exiting, so Q, Q, Q. And then all of these sections are related to each other, right? Because these vehicles that are exiting from each section, they're going to go to the next section. They're not going to go out of the road. Your network, where the vehicles can move, is limited in transportation, so they're supposed to be moving within that network. So the vehicles going out have to come here. The vehicles going out have to come here. And so this is how basically you tie things together. And there's because of this representation, there's a direct mathematical formula that ties all of these together. So that is Q equal rho times V or Q equal K times U. So the number of vehicles that are going out is a multiplication of these, just because the vehicles have to go through that route. And the units also match. The units that I was talking about before, they cancel each other, and they gave you the right unit. OK. These are OK, let's put this aside. Let's try to use that board for a bit. We'll come back to it. OK. Let's see. I have a pen here. I'm going to ask people to help me. Hopefully, this is going to work. Let's see. Not as good as I thought. I should have gotten another one. OK. So we're going to define 3 graphs describing these parameters compared to each other. So let me take you back to this notion and see what they are. OK? And let's be careful with the units. So we have density and speed and volume. OK? So when we have density here, have you learned graphs in school? Yeah, kind of. Who has learned graphs? OK, so based on a variable that you put on the x-axis, this is the y-axis, something changes. OK, so the x-axis could be time, could be anything you want to represent things by. So if this is density and this is speed, OK? So we're talking about a space, and in that space, how many vehicles are there? So that's density. That's vehicles per kilometer. Based on that, how does the speed change? Yeah? The less dense it is, the faster the speed is. So we have some point here, right? OK? When the density is really, really low, it's here. And then when the density is higher and higher, so your activity 1, there were people ahead of you. It was dense. You couldn't go through. What happens with the speed? It decreases. OK. So, and then when there's not even room to walk, what happens? It stops. So this gives you a graph. So this goes down to 0. OK? At a particular density, OK, and this is a special name we're going to discuss. At a particular density, speed goes down. So this is the representation of speed versus density. Now let's see. OK. Now let's do, again, you have density on the x-axis. We're trying to do volume. So remember that volume is at that one point, how many vehicles are going through. OK? So if density is really, really low, if it's Monday morning, 4 a.m., everyone's sleeping early because they have work next day, or at least hopefully they are. We don't have many vehicles on the road. What's the flow like? Is it low? Is it high? Is it? It is? It's a high flow? Well, you don't have anyone on the road. How many people? So if you stand there and check how many vehicles are going through, and you count, over an hour you count, vehicle, 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 and then that's the total, right? So how many vehicles per hour? It's what? 10? So is that low or high? It's low. So with the low density, you have a low volume, somewhere around here, let's say. OK. Then what if the density is really, really high? Or hold on. What if the density increases bit by bit? What happens? Volume goes up, right? So you're being able to let more vehicles go through. So, and when it's zero, it's zero. When you have 0 roads on the road, the volume is 0. So it starts going up. This is supposed to be almost straight. And then, what if the density is really, really high? Yeah?
The volume is low because the speed also decreases?
Yes. So if the density is really, really high, the speed decreases, as we mentioned before. When the speed decreases, the rate at which vehicles are going through also decreases. Okay? So when you're looking at vehicles that are in congestion, then they're stuck after each other. They're barely moving forward. So at one point of time, there aren't many vehicles going forward. Okay? So then you go back to somewhere here. And then when you have traffic breakdown, and it's like a parking lot. By the way, the Don Valley Parkway, the DVP, it's one of the highways that takes you north and south to the downtown area. We often call it the Don Valley parking lot due to this reason, because it has 3 lanes and it's usually not moving in the afternoon. 4 to 6 or 4 to 7 p.m., don't take it northbound. So when it's fully blocked, when no one's moving, it goes to 0. Okay. And then what about in the middle? What happens in the middle? It curves. So there's a point here, okay, which is the maximum capacity. That's the point at which I'm getting the maximum number of vehicles across. Now, this is an important concept because if I draw the other curve, which is with the same density, I had this. Okay? So this is around here. So when I have, I apologize for this, not going to go away. So when I have this maximum capacity, from a transportation engineer's perspective, this is the best utilization of your road. You're getting the most vehicles across using the resource that you have, which is the road. At that point, speed is not the highest. Okay? Speed is almost half of what you had at the beginning. We seem to think, in general, that unless we're going at the maximum speed, free flow speed, which is, let's say, the 100K, things are really bad. But from an efficiency perspective, things are not. Things are the best when we're going at a lower speed because of this, because that is when the road is being used really, really well. If everyone is going at a very high speed and there's no one on the road, if the density is too low, if the density is here, that's not good. You're not using the road to its capacity. It's like having a decent internet connection and not using it. You understand that. Or it's like having a super gaming computer and then just using it for browsing. Yeah, so if you have the capacity, you're supposed to use it. Okay? Now, you're going to see when you start doing analysis of the data from the CP24 website that we have the same problem in transportation as in cloud computing, as in smart grids. Varying demand. The demand is really high in the morning, a bit around noon, and in the evening when people are returning home. How is the demand like at 4 a.m. in the morning? Really, really low, around here. So what happens is during the times when it's really, really low, you're not using the capacity well. And when the demand is really, really high, you start going to this area. So on this curve, this is called, the left-hand side is called the uncongested area, okay, uncongested, and this area is called the congested area. So after you pass the middle point. So the reason for that is you are past this point, and now the more vehicles you add, your flow is going down. You're not making better use of your resources. You're actually having a worse performance. There's one more curve that we should draw, and that is flow and speed. Okay, so how does this curve look? Yeah.
Lower flow, higher speed.
Lower flow, higher speed. So I have a point here. I have a point here, let's say. Okay. What else? If you have a high flow, so you slow down a bit, right? So if you have more vehicles going through, you're going to slow down a bit. Okay. What about really, really high flow? You're shaking your head. Why? If it's really, really high flow, what happens? Cars are what? So on this curve, we know that the maximum, flow and volume are the same thing. Let me clarify that. Flow and volume are the same thing. So maximum flow is this. Okay, so maximum flow is here. And then what? The speed will just decrease. So basically, if you're looking at a point of the highway or any road, and you're counting how many vehicles are going through, if the flow is low, it could be because of two reasons, right? It could be because of either there aren't enough vehicles on the road, okay? So it's Monday 4 a.m. If the flow is, again, too low, it could be for another reason. It could be that you are here, okay? So for the same flow value, you can be very, very low at very, very low density or at very, very high density. So if you are at very low density, then your speed is high. If you are at a very high density, then not enough vehicles are going through because they're stuck there. That means the speeds are very small. So this curve turns back and comes here. For every flow value, you have two values of speed. If I'm measuring 500 vehicles per hour per lane, that could be because there aren't enough vehicles on the road. It's very low density. Or it could be there are too many vehicles on the road. I've moved past this into a congested state, and I'm only being capable of letting 500 vehicles per hour per lane to go through. The others are stuck behind each other. Okay? This is one of the things that I was telling you. These are a bit counterintuitive. But this is real. This is what happens in real life. That's why when a road is congested and you have other vehicles joining the road, things keep getting worse because you start losing the flow that you have. Rather than keeping things at maximum capacity, because of the safe distances that you have between, you need to have between vehicles, you have people slowing each other down, and as you saw, in the first activity, the last person came in 2 minutes and 40 seconds. In the second activity, because you didn't have that congested state, the last person came in at 1 minute and 40 seconds. 1 minute and 40 seconds is a total of 100 seconds. 2 minutes and 40 seconds is 160 seconds. That's 100, almost 160, 170% extra time, if I'm doing the math correctly. 100, yeah. So that's a lot of time. That's almost like more than double time spent. Okay. So this curve looks like this because, and the other curve, which we drew like this, all of these together make a three-dimensional curve. It's not by chance that they have the same shape. Okay? So if you draw density here, so density and then speed. So this curve goes like this, and then this circle continues into here. That's why you have this shape. Okay? So this is an actually three-dimensional curve that we're looking at relative to in three ways using two-dimensional curves. Again, in here, when the speed is high, this side is called uncongested. So the upper part is uncongested, while the lower part is called congested. So because it's the same representation as here. So these three diagrams are called the fundamental diagrams of transportation. Once you understand these, you know transportation. This is what transportation engineers learn in third year at U of T, and everything in transportation is based on these. Okay? So let's go back here. Okay. So density and speed, and this is the midpoint, and this is the maximum. This is called jam density. Okay? This is the maximum vehicles that you can have per unit space. This is the second one we drew, so density, or yeah, this is the second one, so density and then flow. So this is Q max, or the maximum capacity. And here you can see the same value, Kj, jam density. And in here, this is flow and speed. And as we saw, for the same flow value, we can have two different speeds. OK, questions? I want to make sure that all of you understood every single graph here. If there's anything that you didn't understand, please tell me now. So I can ask you to explain these now?
Not very well.
Not very well. OK. OK. Another thing that you're seeing on this curve are these arrows. OK? So this arrow, because this is a flow speed curve, this arrow gives you the density. And this is the density and the flow. So this arrow gives you the speed. Okay, these are the how you can get one from the other curve. And you can, as I said, you can join the three of them together in a three-dimensional curve. Okay, so why did we mention these? As we said, this fundamental idea of adding more vehicles and the flow going down is an important distinction from other systems, from other fields of engineering. in which if I add more capacity, if I add more demand, that doesn't mean that how I'm using the system is better. The actual performance goes down, and for everyone. So congested state on the right, uncongested on the left. Similar case here, uncongested, congested, uncongested, congested. Okay? The higher the density, you'd be in a congested state. So what would city planners, what would transportation engineers qualify as most efficient usage of a transportation system? Can you show me that on the curve? What point is that? What would they like to see?
Is it the middle point?
Yes, it is the middle point. This is where you're using the road up to its capacity. Okay? They do not want to see here. They do not want to see low flow, which is what they do not want to see very high speeds, which is what we think is what your general audience think is the best usage of the road. Because that means more than half of your investment is not being used. Okay, so these curves are defined with these formulas. So let me just recap a few things. Speed is defined as V or U. Density is defined as Q. Flow is defined as Q, and density is defined as K. And these are the definitions for each of the separate functions. The functions are, the first one is a linear function. I'm not sure if you've learned that yet. Some of you might have. So that is defined as a y equal a plus bx, a being the point that it starts at, and b being the slope. So this is at a 45-degree angle, so that's the slope. So Vf, so this is speed, and this is free flow speed. Vf is free flow speed. So at the beginning, at free flow, when you have no vehicles on the road, you have the 100 per hour on a highway, unless you're driving 120, which is usually the case in the area. So that's there, and when the density goes up, then the speeds go down. That's why you have a negative slope, and that depends on the jam density and the maximum flow. Okay, and the maximum speed. You have, if you multiply V on both sides, you get this squared relationship, and that gives you the let's see, the Q. That gives you the Q speed relationship. So that gives you this curve. And then if you multiply by ρ, you get the third curve. OK, so one of the few things that I want you to remember are these. I'm going to give you the formulas later on in the afternoon. You're going to be doing some calculations with these. So here you can see it again. This is called the green shield model. Here's the math for the formula, and shows you how you calculate and you get the formula based on the different intercepts here and here. OK. Now we're trying to identify these points. So one of the things that you find out is the V0, the one in the middle, is half of the free flow speed. So the point at which is the best usage for the system is actually going at half the speed. Okay, which is a bit shocking, but it's true. And the Q max, which is the point that we're seeing as the limit, is rho j Vf over 4. So rho j is the maximum density, and Vf is the free flow speed, and then divide by 4. That's how you get them. OK, so any questions about these concepts? OK, now I'll sit back and someone can explain to me what a smart infrastructure is. What are the elements of a smart infrastructure?
Automated.
Automated. Okay. Optimization. What are the 5 pieces that I was talking about? Yeah.
I know it adapts to each environment in different ways.
Adapts to the changes in the environment in different ways. Yeah.
There's
Sensors. Okay, so you have adjust to changes in the environment. You have sensors. These are the slides from Tuesday. Yeah. You need a computer to analyze that information. How do you get that information? So you need a communication system that sends you that information to the centralized system that optimizes. And then what do you do with that? So you need to send it back. You need a medium to send that result or decision back to a controller, and then the controller will implement that decision to get optimal performance. Okay. I'm glad you're learning and remembering these things. Okay, so now let's think of it from a transportation perspective. You're going to work in your groups of 4 to solve the problem of congestion. Okay? The goal is you want to minimize congestion, and I want you to come up with what you need. So the building blocks that we just mentioned. Okay? What type of information do you need? We talked a lot about the type of important measures in transportation. What do you need to do with them? What processing you need to do for those elements? And how you're going to come up with minimizing congestion based on what we explained there. Okay? I'll give you 15 minutes on this. Okay? I'll give you 15 minutes, and I really want to see this. Now I really want to see this. So I want to see square blocks with inputs and outputs, and what's the actual process that you're doing there. What are you putting in as input? What process you're doing? What's coming out? How do you use that? And remember the goal. The goal at the end is to minimize congestion.